Hi, this is an activity to go over Mod 1, Topic 1, Lesson 3, Activity 3.2, called Equivalent Functions. We are going to be going through the pattern that you see on this page, problems 1, 2, and 3, and how to break down a design so that you understand all the different patterns that may be asked about that pattern. So it says a ceramic tile company creates a new line of decorative kitchen and bathroom tiles. The company sells designs it creates from combinations of small green and white square tiles. The design follow the pattern shown. So we have each design pattern. We have design 1, design 2, design 3 shown to us. And what we're going to do in problem 1 is analyze the tile designs. We're just going to describe as many patterns that we can observe of different parts of each design itself. Then we are going to put those expressions for those patterns in the table for problem number 2. And then we're going to answer problem 3. Okay. So there are 3 things going on here as it relates to problem 1. So it says analyze the tile designs. Here are the 3 things that are going on. There is a pattern for the center gray square. There's a pattern for the 4 corners of gray squares. Then there is a pattern for the 4 rectangles of white squares. There we go. And for each pattern, we're going to break down where it comes from. So for example, the center gray square, and we can choose any design we want. I generally like to look at the last design because it has the most amount of squares. You can kind of see where it comes from. So this pattern has a center square. So we know it's going to be some quantity squared. All right, and it is 1, 2, 3, 4, 5, 6, 7 wide. So it's a 7 by 7. So that may not be enough to really tell us what to do about it in terms of the formula. So let's look at the design 2. Design 2 was a 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, 5 by 5 box. Design 1 was a 1, 2, 3, so 3 by 3. If you notice, okay, I'm trying to get the dimensions of the center, and it goes up by 2. So I know that the sequence of the dimensions of the inner box is 3, 5, 7. It goes up by 2. So I know that the equation is going to consist of a 2n on each side of any of these center boxes. But you have to ask yourself the adjusting number. If you put in the value for n, so for example, design 1, 2 times 1 is 2, but I need the 2 to be a 3 because it's a 3 by 3 square. How does a 2 become a 3? You add 1. And let's see if that's consistent with design 2. 2 times 2 is 4. 4 plus 1 is 5. Design 3. 2 times 3 is 6. 6 plus 1 is 7. So what does that tell me in general? So I'm going to erase the 7 by 7 part. And now this is a 2n plus 1 times 2n plus 1 square. Literally, the area of just the inside of the center part is 2n plus 1 times 2n plus 1 no matter what the design is. So for the center gray square pattern, we are going to say it is the quantity 2n plus 1, but we square it. And those are gray squares, by the way. The four corners of gray squares. All right, so this one, let's erase our previous work so it's a little bit more clear. We're talking about the fact that there are 4 boxes, 4 squares along the edge. So it's good. We know that if we're trying to come up, again, we're trying to come up with a pattern that's just for the 4 corners of gray squares. Or in this case, it's green on your book. We know that the pattern overall will have a 4. But let's look at the design. Each box in design 3 is a 3 by 3. Design 2 is 2 by 2. Design 1 was a 1 by 1. So if I was to take that away, it's always n times n. So no matter what the term number is, it's n times n perfect square. So if I wanted the total amount of the 4 squares that are perfect, it would be 4 times n squared. By the way, on my book says gray, yours should say green. So I'm going to change that to green. All right, the 4 rectangles of white tiles. So let me erase all of my previous work here. Okay, let's look at design 3. Again, we're trying to look for an area of the white rectangle in terms of its n term number. So this is a 1, 2, 3 times, well, we already know from the previous pattern for the center green that this is a 2n plus 1 times 2n plus 1. So we can actually just go back. The height of this white rectangle is n, so design 3, height of 3. And we know from the pattern for center green tile, the center huge square, that this was a 2n plus 1 width. So the area of that green rectangle is n times 2n plus 1. And that's just for one rectangle. Well, there are 4 white rectangles in total in this whole diagram. So we're multiplying this by 4. So 4 times n times 2n plus 1 is, you could also think of it as 4n times 2n plus 1. So this, again, was 4n times 2n plus 1. What we're going to do is simplify every rule however much we can, and we're going to use that into the table below. So for the total green center, that would be 2n plus 1 times 2n plus 1. And remember in class we call this double distribution or foiling. If you were to FOIL this, this becomes 4n squared plus 2n plus 2n, and 1 times 1 is 1. So 4n squared plus 2n plus 2n plus 1, that total amount for the tiles in the middle would be 4n squared plus 4n plus 1. The green tiles in the middle. . For the four corners of green squares, 4n squared can't be simplified anymore. So that is its total. For the four white rectangles, we're going to do 4n times 2n, which is 8n squared, and 4n times 1, which is 4n. So for the four white rectangles, it is 8n squared plus 4n. How that's going to relate down here is we're going to copy that formula into this table and then use a table on our calculator to get these amounts. So there's only one part of the diagram that was for white tiles, and that was for the four rectangles of white squares. And we just found out that the formula was 8n squared plus 4n. The number of green tiles was the center green square, the big one, and the four corners of green squares. So I'm going to take, and I'll highlight what I'm taking here, the 4n squared plus 4n plus 1, and then we're going to combine it with the corner, which is a 4n squared. So 4n squared plus 4n plus 1 plus 4n squared is 8n squared plus 4n plus 1. So again, I'll highlight this. These two amount, and again, this is green. I apologize for the typo for gray. It is for green. That went right here. This pattern for the four rectangles of white was right there. Now for total, you would take green plus white, which we can actually just add going straight down. 8n squared plus 8n squared is 16n squared. 4n plus 4n is 8n, and nothing plus 1 is 1. So for total tiles, the area of any design, it's 16n squared plus 8n plus 1. Now if you're looking at this table, you're like, how do I fill out the rest? We're going to let our calculator do the heavy lifting. I'm going to show you how to do that. So take out your graphing calculator, and we're going to type in each of these equations. So we're going to have 8x squared plus 4x to represent the white tile pattern. Then we have 8x plus 4x plus 1 for green. And then we added them together, and that made 16x squared plus 8x plus 1. Okay, if you're looking at that, yeah, that's a lot going on. We just want the table. So we're going to click second table, which is the graph button. And you'll see y1, y2, y3. So again, y1, that was for the white tile equation. Y2 was for the green tile equation, and total was y3. So we can see here that we can copy over some values. So for design 1, it was 12, 13, and then 25. Notice real quick here, white plus green will give us total, and that should be true. And then ask yourself, does 12 plus 13 equal 25? That's accurate. That's true. Let's go on to term 2. 40, 41, 81. 40, 41, 81. That still holds true. White plus green is total. Then I have 84, 85, 169. Term 4, 144, 145, 289. Term 7, go to term 7, all the way down there. 420, plus 421 equals 841. Term 10, 840, 841, 1,681. So again, key components here, make sure you have the right formula for green, white, total. And then finally, problem 3, what new patterns do you notice? Well, here's the big pattern. I'll highlight this here in red. Notice that green is always one more than white. So we had 13 compared to 12, 41 compared to 40, 85 compared to 84. And you can keep on going. The green is always one more than the white. So let's write that as our final observation for problem 3. I want you to write the number of green tiles will always be one more than the number for white tiles.